In some sense, this everyday watch isn't special at all. I mean, I bought it for $10 at Target. Yet once we look inside, it's amazing. Let me show you. I'd call it the key machine of the modern industrial age. Precise timekeeping made possible things like the global positioning system and our telecommunications infrastructure. Now, this metal container holds the heart of this watch. Inside lies a tiny quartz tuning fork. I have one. Now, it's so tiny that I keep it in this white cap. You can see it right there in the center. Now, although this modern circuitry is vital to the watch, it's based on the same principles of the first clocks built in the 17th century, resonant motion. It's easiest seen in the pendulum clock. This family heirloom, it hung in the living room when I was a kid, uses the motion of a pendulum to keep time. Now, this pendulum oscillates with a regular period that runs a clockwork that translates this motion into movement of the hands. There are many ways to create resonant motion. For example, a tuning fork. This one vibrates 440 times a second. That's an A note when struck. I love that sound. Now, if I slow down the motion of the fork, you can see how the tines move back and forth with a regular period. That's resonant motion, like the pendulum, which can be used to measure time. The quartz crystal I showed from inside this watch is a tiny tuning fork. It vibrates at about 30,000 times per second. But how do you get it to vibrate, and how do you measure its vibrations or record its vibrations? I mean, we cannot get a hammer in there to hit the quartz crystal. The engineer who designed this digital watch used something known as the piezoelectric effect to make the small tuning fork vibrate. You can see this piezoelectric effect most easily with Rochelle salt. Here at the center lies the crystal. I've attached 2 electrodes made of tinfoil and strung wire from them to a small ball. Watch what happens as I strike the crystal with a hammer. As I deform the crystal, it generates a current. The reverse also happens. If you place a voltage across the crystal, it deforms. This is how the quartz tuning fork in the watch is pinged. A voltage from the battery sets it in motion, and then the watch's circuitry measures the current fluctuations that represent the resonant motions of the tines. Quartz is ideal for digital watches because of its outstanding physical hardness and mechanical and chemical stability. And that stability makes this watch work nearly anywhere on Earth and under all but the most extreme conditions. One more interesting thing about these digital watches is how these tiny tuning forks are made. On a production line, engineers must make these quartz tuning forks so accurate that they vibrate at 32,768 times a second, plus or minus 1/600th, about 2 parts per million in frequency. If that frequency differs by 1/600th, the watch will be off by more than 1 minute a year. And to see how they tune these forks, look at the ends. You see deposits of gold at the ends of the tines. These are added to make the fork's vibrational frequency too low. On the production line, a laser zaps tiny bits of the gold off until the frequency of vibration is just right. It's a wonder that these magnificent engineered objects are so inexpensive. I'm Bill Hammack, the Engineer Guy.